to be valid, we need point-wise existence. Like we need a function ut to be continuous at every point xt. Okay. Um, so that is this is the given equation for our solution to be exist. Whatever solutions are permitted, solution functions are permitted here, we will have to be differentiable with respect to t, and also the derivative should be continuous at points xt. Okay. So that means u should belongs to C1 continuously, once continuously differentiable with respect to t. Okay. For this, to be this to be defined, we need u to be continuously differentiable once with respect to t, that variable t. So here, so we have like this situation. We have x variable and y variable, and let us say the x limits are the domain of x is a to b, and t is any positive t is any positive real number. So the domain is like this. Our function u is defined on a domain like this. Okay. So what is the next thing that we, instead of dealing with this, there is a strict restriction on u should be a continuously differentiable function with respect. Can we allow a larger class of functions here? So what is the formulation? That is weak formulation of the given weak formulation of the given PDE. Okay. So for that, how to get the weak formulation of the given PD? For that, we are what we are doing is integrating the given integrate both sides. Integrate both sides with respect to integration with respect to x. Okay, that is the limits are a to b, x limits are a to b, and we are integrating dx. So integrating and yeah, let us have consider like this equation with integration like this. So what will happen now? I can take this integration inside this derivative. What is ut? Ut is nothing but del u upon del t. So what I'll do, this differentiation, I can exchange integration and the differentiation for certain special functions. So if suppose it is allowed, we can have differentiation with respect to t of this function a to b u x t dx. Integration is with respect to x. So I will have the derivative coming outside and integration is inside. Okay. And the previous function was f, the flux function is f of u, and it has a derivative with respect to x, and integration is also with respect to x, so they cancel each other, and we have endpoint evaluations of, so u b t minus u a t is equal to 0. So if you see now here, for this equation to be valid, for this equation to be valid, what is the requirement on this one? We are not requiring that del u upon del t to exist and continuous. We are not requiring this much, but we are not demanding that u should be differentiable with respect to t, and also continue the derivative should be continuous, but we are considering something integral of u's. Okay, this, if you define this function as gt, what is the relation between g and u? G is something like integral of u. Okay, we are not demanding that u to be differentiable, but something like integrals with respect to x. So whenever there is a because we will have problems with variable x, we'll have problems with. So what we are doing is we are allowing a larger class of functions uxt, that is even those with jump discontinuities. Okay, even functions with who jump discontinuities in the variable, in the x variable. Okay, we are not demanding that u should be differentiable, etc., with respect to x, but even discontinuous functions, even discontinuous functions also we can allow, because in reality we will have shock solutions or discontinuous solutions. So how to handle this? That is why we are calling this as a weak formulation. And yeah, and now we consider this equation that is yeah. Now the question is, we can solve the given PDEs which has discontinuous solutions. Discontinuous, I mean jump discontinuities. That is for example, we can have if we have a function like this, the step function. So we have the left limit existing, right limit existing, but they are not equal. Okay, so both the left limit and right hand limit exist, but they are not equal. That's such sort of functions we are calling as discontinuous solution. So let us solve an example where we can understand everything clearly. Okay, suppose you have the same Burgers equation, u plus ux is equal to 0, with the initial condition. This is the PDE, and initial condition is u x comma 0, that is at t is equal to 0. We have, let us call this function as hx, and this as to begin with, the initial profile itself is discontinuous. That is, we have let us say 0 when x is positive and 1 when x is negative. that is a function of this type. That is, when x is negative, it is 1, and when x is positive, it is 0. A function like this. Okay, this is our hx. Yeah, this is our hx. So how to solve this problem? So now, what is this? Again, we adopt method of characteristics. Method of characteristics. What is method of characteristics? That is, it is to convert the given PDE into a system of ODEs. So if you see, we have dx upon dt is equal to 1. That is comparing with a u x plus b u y is equal to c. Okay, that is in our example, it is like u x plus uy is equal to 0. Okay, so this is our a. So this is our a, that I am calling, because z is equal to uxy is our solution, so I can call u as z. So this is z. This is the first characteristic equation. Second is here it is 1. So dy upon dt is equal to 1, and dz upon dt is equal to 0. Okay, these are the three ODEs we obtain, because these are the our tangent. This is the tangent vector x dot y dot z dot. This t is different. This whatever ut is different. This t is just, I am using it as a parameter. I will get rid of this parameter later on. So we have solved already this sort of equation in the previous class. So what is the solution? Solution is z is equal to uxt is equal to h of x minus ut. Okay, this is our solution. So here, what is our h function? H function is 0 when x minus ut is equal to is greater than 0, and 1 when x minus ut is less than 0. That is something like x greater than ut and x minus. So now here, what is the next important step is why this problem of discontinuity comes, because see, we have 1 and we have 0. This is our initial profile. Okay, so what are the characteristic curves? Characteristic curves. Okay, characteristic curves are those curves where we obtain by solving the characteristic equations. Solutions of characteristic curves are solutions of characteristic equations. Okay, so now what is the first step? Step 1 is notice that first thing is notice that characteristic curves intersect. So why characteristic curves intersect? So what are the characteristic curves now? Dx upon dt is equal to z, that is hs. So integrating, we'll have zero is equal to s itself is equal to c1s. So this is our s. Okay, and next equation is dy upon dt is equal to 1. So solving this, you get y is equal to t. So here we get so xst is equal to x is equal to hs times y plus s. So now put what is hs. Hs is equal to 0. So that means x is equal to s. These are the when x is greater than 0, x is equal to s are characteristic curves. And when x is negative, hs is 1. So s is so what are the curves? X is equal to s plus 1. This is y plus s. Yeah, y plus s, or t plus s. In the variables t, we have t plus s. Okay, so now now draw these lines, draw these characteristics. So how to draw these characteristic curves. So this is our x variable, and this is our, like, let us say this is our t variable. Okay, now what are the lines for give x is equal to s? These are our lines. X is equal to, so these are the lines x is equal to s. For each s, x is equal to s lines. These are the characteristic lines when x is positive. And when x is negative, t plus s. So take an suppose s is equal to 1. S plus, what is the line? S plus 1. X is equal to t plus 1. So this is like, we have slope. This is like y is equal to mx plus c type equations. So t is equal to x minus 1. Okay, so it will have a slope 1 and intercept x intercept 1. So x intercept minus 1. So what is that line? So this is our line, x is equal to t. And for x is equal to 1, this is minus 1. So we'll have the line, the slope 1, and intercept is minus 1. So next is minus 2, minus 3, like that. So what is happening here? These characteristic lines are intersecting. These characteristic lines are intersecting. Okay. So why these characteristics, why they are called characteristic lines? Because they determine the solution. We define the solution as a constant on each characteristic lines. It will take one value on each characteristic line. So when they intersect, which value to take? Here solution is 0, and here the solution is 1. So which one to take? So there is a problem here in this region. In this region there is no problem. In this region there is no problem. But here the characteristic lines are intersecting. So how to resolve this issue here? So that is why we need these equations. That is why we need. That is why the shock is coming. Shock is jump discontinuity. There are two values. U is equal to 0 also. U is equal to 1 also. So which value to take? So we have to determine something called shock propagation we have to determine shock propagation curves. So now our next goal is to determine shock propagation curves so that we can have an agreement that if the discontinuity is propagating along this curve, so towards the left you will have u is equal to 1, towards the right you will have u is equal to 0. So there is an agreement. So determine this curve so that we can, towards the left we can have u is equal to 1, and towards the right we can have u is equal to 0. That is, the characteristic curves will be like this and like this. So we can avoid the intersection. So how to determine this shock propagation curve? So let us say that, yeah. So with this, after this we'll stop. What is an equation for shock propagation curve? So since there is, this is our equation. This is our weak formulation plus f of u b t minus f of u a t is equal to 0. This was our weak formulation. Now, suppose there is a jump at x is equal to, let the jump be at a point x is equal to, let us say, some xi for fixed t. Let us say fix the t for fixed t. Okay, that is, we are fixing t, and this is our x variable, this is our u. So t is fixed. So this is our point xi t, and it is in the interval AB. So at this point x we have a jump, that is, solution is some nice at up to this point, and there is a solution is nice at this point, but there is a jump at this point. So how this jump, this discontinuity propagates, that's what we want to find. How this, as time proceeds, as t increases, t varies, how this xi t varies. We want to find the curve xi t. Okay, x is equal to xi t. Find the curve x is equal to xi t. So how to find the, so now because there is a jump at x, split the equation integral, split the integral into 2, a to xi t u x t dx. Sorry, yeah, plus t xi t to b dx. Okay. So earlier we had a to b. Now we are splitting because we have no problem from a to xi t and xi t to b. But at this point xi t we have a problem. So we are splitting like this, and of course plus plus the other things are also there. Plus f is there is equal to 0. So now how to yeah. Now what is the next step? So what is the what is the equation now? What is the equation? Final shock propagation equation. So now do the differentiation. Do the differentiation with respect to t. So the here is the t is in the t is in the limit of the integration also. T is in the integrand also. So Leibniz rule, apply Leibniz rule. So first xi prime t and u at the left, the differentiation of u. So what is the Leibniz rule? Apply Leibniz rule. So we have apply Leibniz rule because we have something like differentiation where the variable is at in the limit also, variable is at the integration also, integrand also. So we have the variable here also, we have the variable here. So what this will be xi prime t into what? First I am differentiating with this thing, and what I will do, I'll what is the next? This is our u value of u at the left value. That is because we cannot substitute directly this one. So we have u l at ul at xi t. What is the meaning of this? What is the meaning of this? What is the ul of this? Is limit limit x going to x going to the left side, xi t minus left hand limit of the derivative, okay, of the. So this is of u x t. So this is the left value, and similarly we'll have the right limit minus xi prime t minus xi prime t and we will have minus xi prime t into u right side value at xi t t. Okay. Plus we'll have integral a to xi t, the derivative of this with respect to t, xt dx. And we have also the other value xi t to be del u upon. First, the derivative will fall on the xi, and the next derivative is falling on the t, on the u, xt dx. So now, what to do now? Let x tends to xi t. Now limit x tends to xi t will give us. So what will happen is, so now let a tends to xi t, and b tend from the right hand side to xi t. What will happen? These values will become zeros. Okay, and as a tends to xi t and b tends to xi t, we have, this implies finally we'll have xi t is equal to xi prime t is equal to, we'll have finally we'll have this equation, psi prime t is equal to f at ur minus f at ul upon ur minus ul. So this is the equation. This is the equation which will determine the shock propagation. So this will determine the shock propagation. So so you have understood now this one, how we got this one. Yeah. So at this point, I think we should stop the class and yeah, continue in the next. Please go through the notes, and also book. I will put it in the Moodle, McOwen book, because this is like we'll have examinations, open book exams, so you don't have to understand every detail. The details are you have to understand, but you don't have to memorize everything. You have to know what is happening, because the book is with you, and when exams comes, it will be new problems, new derivations you have to do. So using the book itself, you can attempt the exams. So that will step by step understand everything. Okay. With this, I will stop here. We'll continue tomorrow, and I will start from again the how to obtain the shock propagation curve, and give the final solution for this problem. We will do other examples also. So I am now stopping here.